All right, let's pull back the curtain on the hidden world that creates, well, literally everything around you. Your phone, the chair you're sitting in, your coffee mug. We're going to dive into the absolutely fascinating field of manufacturing engineering.
To make this real, let's follow the journey of just one humble product. Picture a simple metal wrench. Seems basic, right? But its creation is this amazing multi-step engineering story that starts with just a lump of raw metal and ends up as a precise, super durable tool.
So how do we get from a block of metal to something that even kinda looks like a wrench? Well, the very first step is to create its basic rough form. This is all about just getting the general shape right. Nothing fancy yet.
One of the most common ways to do this is through casting. It's an ancient technique, but it's still totally fundamental today. Honestly, think of it like making ice cubes. You pour liquid water into a tray, it freezes, and boom, it takes the shape of the mold. Casting is the exact same idea, just with super hot liquid metal.
But here's the catch. You can't just make the mold the exact shape you want. Oh no, engineers have to think way ahead, adding what they call allowances to the design. See, metal shrinks as it cools, so the mold has to be a little bit bigger. You add a slight taper or draft so the part pops out of the mold easily. And you leave extra material on surfaces that you know you're going to cut later. It's like playing a game of 4D chess with physics.
So how long does it take for that molten metal to actually solidify? Well, engineers have a rule for that. It's called Chivaranov's rule. We won't get bogged down in the formula, but the core idea is just beautiful and simple. It's all about the ratio of a part's volume to its surface area. A compact, chunky part like a metal ball has a ton of volume but not much surface area for heat to escape, so it cools really slowly. A thin, sprawling part, it cools way faster.
Okay, so another way to get our rough wrench shape is by physically forcing solid metal into a new shape. This is called forming, and this presents a huge engineering puzzle. Do you heat the metal up first? That's hot working, which makes it way easier to shape but leaves a kind of rough finish. Or do you do it cold? That takes a lot more force, but it actually makes the final part stronger and much more precise. The choice really depends entirely on what that final product needs to do. Okay, so now we've got this rough, wrench-shaped piece of metal. But it's not a tool yet, not by a long shot. The surfaces are rough, the dimensions aren't exact. The next stage is all about adding that crucial element, precision. And this is where machining comes in. If casting is like pouring a sculpture, machining is like chiseling it. It's a subtractive process. We take our rough part and use these incredibly hard cutting tools to just shave off material layer by tiny layer until we get the exact shape and smooth finish we need. It's industrial sculpting. So what are the chisels in this industrial sculptor's toolkit? Well, there are three fundamental machines. You've got the lathe, which spins the workpiece to create round and cylindrical shapes. Then there's the milling machine, which uses a spinning cutter to carve out flat surfaces and all kinds of features. And the drilling machine, well, that one's pretty self-explanatory. It makes holes. Pretty much any machined part you can think of is made using some combination of these three basic operations.
And here's another one of those critical trade-offs, captured by something called Taylor's tool life equation. It describes a simple but really profound relationship. The faster you run your cutting tool, the exponentially shorter its lifespan becomes. So manufacturers are in this constant balancing act between the need for speed to make parts quickly and the cost of constantly replacing worn-out tools.
Now, our wrench is a single piece, but let's be real. Most products, from cars to airplanes to skyscrapers, they aren't made from one giant block of metal. They're assemblies of many different components that all need to be joined together, and joined together permanently.
The absolute king of permanent joining is welding. At its core, welding is just controlled melting. You use intense heat, usually from an electric arc, to melt the edges of two separate pieces of metal. You might add some filler material, and as it all cools down and solidifies, those two pieces literally become one. This is how everything from ship hulls to bicycle frames are fused together into a single, incredibly strong structure.
Okay, so we've got our processes down, but this brings up a much bigger question. So far, we've focused on how to make one perfect part. But modern manufacturing isn't about making one, it's about making millions. And this shifts our thinking from the workshop to the entire system. How do you possibly orchestrate this complex dance at a massive scale, efficiently, on time, and on budget?
This brings us to the final and maybe most important piece of our puzzle, industrial engineering.
If the steps we just talked about were the muscles of manufacturing, this part is the brain, the part that choreographs everything for maximum efficiency.
The heart of this whole operation is something called production planning and control, or PPC. The best way to think about it is as the factory's central nervous system. It's the system that sends signals out to every department, coordinating the flow of materials, machines, and people to make sure everything happens in the right order and at exactly the right time.
PPC breaks this massive coordination problem down into 4 pretty logical steps. First, there's routing. That's where you define the exact physical journey a part will take through the factory, from machine to machine. Second, you do scheduling, which is basically putting that journey on a master calendar. Third is dispatching. That's when you give the official go command to actually start the work. And finally, and this is crucial, there's follow-up, which is the feedback loop, constantly checking to make sure everything is actually going according to the plan.
You know, this quote from James Dyson just perfectly captures what this is all about. Manufacturing is more than putting parts together. It's coming up with ideas, testing principles, and perfecting the engineering, as well as final assembly. It's not just a repetitive, mechanical thing. It's this incredible blend of physics, material science, systems thinking, and a whole lot of creative problem solving.
So, the next time you pick up a simple tool, or sit in your car, or use your laptop, just take a second to think about the incredible, invisible journey it took to get to you. What part of your world was forged, cast, machined, and scheduled into existence today? Thanks for tuning in.